The recorder is started. Um, all right, so we are kind of flexible as far as what we can talk about today. I remember last Thursday, at the end of the class, I said, if you have anything that you want me to explain, like you come up with a program and you want to see how it is implemented in assembly, I can probably do that. Um, so do we have any questions, any suggestions? Anyone has a program that you want me to take a look at and then do the implementation? Yes. Yes, we can do that. Okay, so we'll start with that. Okay, but I do want to get your brain started. If you can think about any program that you want me to illustrate, using assembly code, as long as it can fit in the TTP, I can probably do that. Okay, so keep that in mind. Okay, as I try to explain the solution of the recursive assignment. So let's go ahead and go to the recursive assignment, and we can also talk about the exam on Tuesday as well, if people want to talk about that. All right, so we will go to the recursive assignment. Mm, Yep, there we go. And I'm not sure where the zip file is. I think it is in that one, but we'll see. Okay, yep, it is right here. So fib.zip is containing the files that you need. So we'll go ahead and download that first. And basically, I want to make sure that I have the same starting point as you do. So this way, the process is parallel to what you need to do. So I'm going to make a new folder. We'll just call it fib. It's already there. Go to fib. Oops. Go to fib. Well, it says it's already there because the file is there already. So we want to remove the file, make it a folder, go to the folder, unzip the file itself. All right. So we're going to start with the C code. Okay, the C code does compile. And it is good to have the C file to compile because then you can double check whether your assembly code is doing the same calculation as the C code. So we will. Are there any questions about the C code before we start on the assembly code? So is there anything in the C code that you want me to explain before we move on to talk about the assembly code implementation? Okay, I'm not seeing any questions. Okay, all right. So if there are no questions, we are gonna start with the assembly code. And let me see how we can do that. So the assembly code has main already done for you. So basically the main program is already here. And what you need to do is only to finish up the assembly code portion. So what we want to do, the first thing we want to do is to figure out what is going on the stack. In other words, we want to have a layout of the stack itself. So we're going to go to the share folder, okay, do the typical thing that I do, start a new spreadsheet for today. So this way, everything that we talk about is going to be, logged in the spreadsheet. So we go to Google Sheets and name it in today's date, 2025 1120. Yep, here we go. All right, so we do the usual thing. Okay, this time I'm going to use a decimal on all the way to the left-hand side and do the hexadecimal next to it. Just a very slight change of the format. Okay, so we'll need eh, let's say a few bytes here. Okay, and then these would be the hexadecimal representation of that. Okay. And then we want to describe, what that location is. So column A, for the most part, is not really needed, but I'll just keep it here so that we can translate, from hexadecimal to decimal kind of more easily. All right, so as usual, this is the returned address from main to the entry code, because if you look at the implementation. This is the entry code. It has no name. It is not a function. It is simply where execution starts by default. So that's why we call it the entry code. And I can even figure out what is .6 plus at this point. This is byte 0, byte 1, byte 2, byte 3, and then when you add 6 to 3, it would be a 9. So just from looking at the code and knowing how many bytes, for each line of code, I can already calculate .6 plus in this case is a 9. So we know that the return address is 09 as in hexadecimal. And then we go to main. Okay, so we switch to main over here. Main only has one local variable, which is x. It takes up only 1 byte. So that means, if I do everything correctly, this would be x of main. And we don't know the value at this point, so we'll just use two question marks over here. And then we call the function. Okay, so we look up the code to call the function. So the code to call the function is, we put a 3 into register A, we push A on the stack, so that would be the 3. So now we switch back to here. This is going to be the value of 03 in hexadecimal. It is the only argument that we need to pass to F. So I think I called it N. Okay, the parameter name is N. So this is N of F. And then we have the return address. Okay, so we also have to push the return address. So line 23 to line 25, is pushing the return address on the stack. Now this one I cannot really do. I cannot count the number of bytes or know the return address quickly, but I can still do it. Okay, do you guys want to see how to do it? In other words, what happens when you have to write your code without an assembler, because then you have to count everything. Okay, so let's do it. Okay, so we have 0. Okay, let me use the mouse pointer so to help me count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 to line 23, 18, 19, 20, 21. This would be location 22, which is in hexadecimal 16. Okay, so that's just me, doing my little mental math here. So this would be 16 in hexadecimal, and it is the return address from function f, which is the first invocation of function f, back to main. All right. So that's what I think should be on the stack, when we run the algorithm up to the entry point of F itself. So now we go to F and we go like, okay, all right, let me just double check to see if I have a good understanding of what should be on the stack. Because if my understanding of what is on the stack is incorrect, then I should not start coding. Okay, I should be able to explain everything first, make sure that TAC does not screw up the implementation of main and also the call to F, because otherwise, you know, your function may not work just because I did not set it up correctly. All right, so let's go ahead and make sure we save this. And then in a separate window or separate tab in my terminal, I can now go to Documents, CISP 310, Reefer Spider, and then we just do the usual thing. Okay, so we want to go to the FIP folder this time, and it is fib.ttp.asm. And there we go. So after this, the first thing I would do is to go to the assembler and double check to see if my calculation of the return address is correct or not. So the assembly is finished, object code is good, simulation is also done. All right, so now we can switch back to the assembler. And then the first thing, as I said, I would go to the Assemble tab to make sure that I have the return address done correctly. Now, there are two ways to verify that. I can go to the location, to see, how the location that's supposed to store the return address to see how it's updated. But I really want to do this kind of like step by step. So I go to location F6 and run 8. So I did my calculation somehow incorrectly because I thought it'd be a 16 and it's actually a 19. Huh. Did I forget to include the JMPF as 2 bytes? Well, since everything is recorded, I can actually go back and check my own counting. But anyway, it is supposed to be 1/8 and not 1/6. I was just curious of how I came up with 1/6 over here. It could be just the base conversion. It could be the base conversion. Well, anyway, I can go back and perform a self-diagnosis later. Okay, I don't want to waste your class time to do that. So anyway, this is what I should be seeing, okay? So even though I miscalculated the return address from F to main, which is the whole point of having an assembler to do it for you, right? Um, this is what I should be seeing at the halt instruction right now, which means I should see an overwrite to location FF with a content of 09, a 03 to overwrite the location FD, and a 18 to overwrite the location of 1C. And instead of switching between the two screens like crazy, I'm going to kind of do the easier way to do this. I'm going to use a small window. So this way, I don't have to switch between the screens. So now we switch back to the assembler. We go to the trace, and then we look up how memory content is overwritten. So this is a 08 instead of a 09. I miscounted also with that one, but it is definitely a return address. And then we push a 00 on the stack at location FD instead of a 03. Wait, okay, this cannot be right. This cannot be right. I think I have to submit it one more time. There's a missynchronization between River Spider and the assembler. Sometimes it takes twice, like a second attempt to get it to work. All right, so I think this time it should be correct. Yep. Okay, much better. So location FF is getting 09, and then we have FD being 03, and then the next location should be 18. So now I have, a full account of what is on the stack, and everything is now as expected. Are we doing okay so far with this particular step? Okay, so this step is not 100% necessary because I checked the code already. From your perspective, you can go like, okay, I don't have to do this step. Well, the answer is no, you did not have to. But doing it is a form of studying. Okay, so in this class, like in all of my classes, I don't really tell people how to study. I can make suggestions of how to kind of study and understand the material, but ultimately it is up to each individual to decide whether what I'm suggesting is a good way to do it or whether you have a better way to do it. Okay, that is entirely possible that you have a different way, but it's also better to study for this class. All right, so now with this done, I am also going to go back to the map here because I want to really identify which parts are um, the call frame of main. This is the call frame of main. It has the return address and the local variable, but there are no parameters. But it is nonetheless, this is the frame of main. So I'm just going to color code it a little bit here, just so that it stands out visually. And then these two locations would be the frame of the first invocation of F. So let me color code it first, and then I'll further explain, what I meant by that. Because F is recursive, so that means you're going to have multiple invocations of the same function. When you look at recursion from Cisp 360 or any other class, okay, including 400 and 430, it is not visible to you that each invocation, with each recursive invocation, has its own frame. Okay, the parameters, the return address, they occupy unique locations between invocations. But in assembly language programming, because we now have a full visibility of the stack, it becomes visible. Is that okay? All right. Okay, so now that we know that everything is set up correctly, I am going back to the program. So in other words, I'm trying to pretend to be you, working on this program, and I'm going to strategize of how to implement this program. And to do that, um, I need to copy and paste the code of function f. So I'm going to go to fib.c. Oh, okay. Go to fib.c and then just copy, well, I can just copy all 4 lines over here and just gonna paste right here. Okay, that's fine. And then comment out each line. I could have just used the VI command to do it, but 4 lines is it's okay. There we go. All right. So with these 4 lines, the first thing I would do is to kind of introduce the offsets. So we're going to say f underscore LVS is 0 because there are no local variables here whatsoever. And then f underscore n, which is the offset to find parameter n from the base of the frame, is going to be f underscore LVS 1 plus. That is always the case. Okay, if we had local variables, it would still be f underscore LVS 1 plus. Okay, because we have to allocate for all the local variables first, and then we have the return address. That's why we have the 1 plus. And then we have all the parameters on top of the return address. Okay, so are you guys understanding what I'm talking about? Okay. So these are just kind of handy items, and you can actually visualize why they're useful because the base of the frame is here. Okay, this is the base of the frame. So if I need to know where to find parameter n of f, it is 1 byte on top of that. That's why the offset of f underscore n is exactly 1 because the stack pointer, well, it does have to do with the stack pointer, pointing to this location right at the entry point of the function, but it really has to do with the base of the frame being at location FC, and then the parameter is at location FD, and it is off by 1 byte. And that has to do with how parameters are pushed, or arguments, I should say. It has to do with how arguments are pushed, and then we push the return address. So who dictates that? It's the caller-callee agreement. Okay, so everything goes back to the caller-callee agreement. Now, when we deal with structures, then we have some additional stuff to talk about, but this has nothing to do with structure. So everything in this program has to do with how the caller and the callee communicate with each other based on the agreement. All right. So now we go back here and go like, this program is a little bit complicated. I am not going to implement the full thing, so I'm going to have to kind of get rid of this halt instruction here and make an actual return. Okay, so we'll just do the usual thing. Okay, now I said usual thing. You should still remember what each instruction is doing and why it is here within the sequence of returning from the callee to the caller. Okay, so if I were you, now I can just say, okay, this is the usual sequence because I've been doing this for many years. But from your perspective, if you still are kind of like, okay, I know there's a particular pattern to returning, but I'm not really sure why that is the case, figure that out. Okay, because it is super important to understand what each line from line 18 to 20, what each line is doing and why it is there. Okay, so that is actually really important. All right. So first thing first, I'm just going to say I'm changing the C program here, and it will just return, say, 42. But 42 has been overused. Okay, so we're going to say, okay, what about 42 in hexadecimal? What is the decimal value of 42 in 42 in hexadecimal? That would be 4 times 16, which is 64, plus 2, which is 66 in base 10. So I'm also using this opportunity to practice base conversion. Okay. Um, so base conversion is one of those things where you go like, okay, if once I'm out of your tax class, I don't need to understand base conversion anymore. That is not true. As you will find out, that is not true at all. Okay, base conversion is really important as a part of computer science and also software development because that's how you can understand how numbers, values are represented inside the computer. Super important. All right. So this is the program. Okay, so I'm just going to leave a note to myself. Okay, to do remove this once I verify the code is quote unquote working. Okay, because what I'm doing here, this is equivalent to saying just return 66 in C++. That's all I'm doing here because I want to make sure that the code does return, the value is returned back to the caller is storing that into local variable x of main. So I want to make sure the rest of the program is working as well. Are we good so far? Yes. Okay. All right. So let's do this. Making sure that I save the file first, and then we'll go run the program again. So this time, what I should expect, okay, if I go back to the spreadsheet, this time what I should expect is this location, FE, is going to be overwritten with 66 in decimal or 42 in hexadecimal. Okay. The Hitchhiker's Guide to the Galaxy never specify whether 42 is in base 16 or base 10. So I have the freedom to choose what base it is supposed to be in. Actually, did they say 42 or did they just show the number 42? 42. They said 42. Darn it. That means it's base 10. Alrighty. So let's get back here. And I'm just going to skip all the way here. Haha. Okay. We are indeed storing 42 in hexadecimal into location FE, which we now know is local variable x of main. So that means the rest of the program is working correctly, okay? Which is important, okay? Because this is going like, okay, if the program stops working, it has to be some code that you introduced. Okay, so now we switch back to the C code, okay, and we go like, okay, we can now return 66 by itself, okay. What about if I just change it to return n by itself? Because I want to make sure that I can actually get to n. So now the question is, how do we do that? So now the code becomes LDI, okay, and f underscore n, a f underscore n, that's the offset from the base of the frame to local variable, I mean parameter n that is on the stack because it's an offset. And as it turns out, at this point of time, local variable, not local variable, at this point of time, the stack pointer points directly at the base of the frame. So I can just add the stack pointer to the offset in order to get to the address of n. But that's just the address. I need to do an indirect, okay, just so that I can get to the value of n, okay, and we'll just, okay, fine, we'll just do this much, okay, because these 3 lines is supposed to implement line 18 already. So if I pass 3 as an argument to function f, it won't do any recursion. It won't do anything fancy like line 14 is suggesting. It simply returns 3 back, and I should store a 0, 3 at location fe in this case. So you might ask, so what is the whole point of doing this? Because I need to make sure that I can access n. Okay, I know how to get to n. So let's go ahead and kind of save this code and run it. So you can see this is a very iterative process, okay, which you have the luxury of practicing, okay. When I was learning, say, Pascal, okay, or even assembly language programming, the computational hardware was not common. When I learned Pascal, it was on a mainframe computer. If I need any printout, I will have to submit a print job, and then maybe in 15 minutes or half an hour, I can walk downstairs to the lab and actually get my print out, as a fan folded paper. Okay, most of you don't even know what I'm talking about. Fan folded paper? No? Okay, I see some nods, but most people shake their head. All right, so I cannot resist this. I have to show you. Okay, fan folded paper. I think it's called fan folded. It's not that. Um, Printer paper. I might have gotten the term wrong. All right, well, I'll look it up later. It is a distraction. Okay, I apologize. All right, so Oh, we can do back here. All right, so we want to run the code again. Did I do that? Let's do it again. Go to the assembler, and yes, I actually did it. So it's storing a 03 back to location, the location corresponding to local variable x of main. So the program is working. I know I have access to n. Okay, so what is the next thing to do? Well, the next thing to do is to implement the conditional statement, the ternary expression. Okay, so if I go back to the code here, you can see that, oh, ultimately, this is what I want to do. But this is a little bit complicated, so I just want to do maybe just this. Okay. In one case, I would just return some random value. Okay, let's say 52 in decimal, and in the other case, I want to return another random value of 21. Okay, for no particular reason. Okay, but this makes sure that I can verify, that I can evaluate the condition, and then I can go to the correct branch depending on whether n is less than 2 or not. Okay, so it is actually of really important value that I do this first, because if I can't do the conditional branch, then there's no point in trying to work on the recursive call, because there's just no point. Okay, so this is what I'll do. Okay, so now we go back here, and I can just extend the code, okay, because having n already stored in register A is kind of handy. Okay, we can now say, okay, let's go ahead and compare that to 2. So we'll go ahead and say, okay, LDI B with 2, and then do the compare. So when you use a compare, you have to remember it is a subtraction operation. Then you have to remember which way do we want to do the subtraction, because we have JCI, right, which confirms that one thing is less than the other one. And then, so it depends on how you want to structure this. There are two ways to do it. You can say compare, in this case, AB, and then you have the JCI to the then branch in that case. Or you can compare BA, and then you can JCI to the else branch, but then you also need a JZI also to go to the else branch. So it's up to you, one way or the other. Okay, so let me explain what I mean by that. So let me just use the other approach, the second one, which is compare, we reverse the order. So we basically compare B, A in this case. So we are computing, we are basically asking, is 2 less than n or not? Okay, we are basically reversing the comparison. So now we can use JCI. So if 2 is in fact less than n, then we go to the else branch, which is the recursive case. So I'm going to go to f else 0, but we also have a JCI to f underscore else 0. And let me finish the branching first, because if I do not perform either of the conditional branches, this is the then branch. And then after the NAND branch, I need a JMPI to end if 0, because this is if it's equivalent to an if then else. So if you have an if then else, the then branch needs an unconditional branch around the else branch. So this would be the else branch, and then we have f underscore end if 0 over here. All right. So let me go ahead and comment line 24 and line 25. So line 24 is saying, okay, if 2 is less than n, go to the else case. Is that correct? Okay. In other words, if you look at the original code, which is here, is it basically saying if n is greater than 2, we definitely want to go to the else of the ternary expression. If, okay, let me repeat it one more time, okay? You just have to reverse the comparison here, okay, and then reverse the relational operator. So we are asking, if n is greater than 2, should I go for the then case, or should I go for the else case? If we should go to the else case. Huh? Yes, so this is greater and this is equal. So we separate the greater than or equal to into two parts. There you go. Yep. So make B a 1. So now so if we make B a 1, then we are asking whether n is greater than 1. But then what about the case when it is 1? Oh, so you're saving the Z flag. You're saving the JZI. Okay, I see what you mean. Yep. So in this case, if you change the 2 to a 1, then you don't need line 20. You basically have to get rid of line 25. But that takes a little bit more thinking, and then your assembly code is no longer a one-to-one correspondence to the C code in terms of the values. So if it works, it works, right? I understand what you're saying. You're basically changing the constant that we're comparing to in order to save a conditional branch instruction, and that works. But I just want to keep it as close as possible to the original code. So if it specifies 2 here, I just want to specify 2 over here as well. Okay, all right. So now, we want to say, okay, what are we supposed to do in the then case? In the then case, we're supposed to return 52. Okay, so we say LDI A with 52 in decimal. And then in the else case, we're supposed to return what? 21. So we put 21 into here. So now I can just rerun the program because right now n is 3. 3 is less than 2 is false. So that means it should return a 21, which also means location FE should be updated to in hexadecimal 15, okay? Because 21 in decimal is 15 in hexadecimal, because 21 is 16 plus 5. 1 of 16 plus 5 of 1, essentially. Okay, so save the code, run it. Okay, save again, and then we just run it. So now we go back to this code, and it's going to move this down a little bit, just because the program gets a little bit longer now. Yep. Oh, this is. Oh, okay. It got the job done. Okay, it is 1.5. Okay, so the program did work correctly, but I only checked one branch. I should probably check the other branch. So when I check, there are two things that you need to pay attention to, and this really has to do with using AI as well, okay? Because vibe coding is a thing, okay? And when you're testing the code that is generated by an AI, how do you test it? You have to look for the boundary cases. In this case, the boundary case or the largest value of n that should point it to this way would be a 1, okay? So we want to test that too. We also want to test 2 because it's the smallest value that it should point to the 21. So now we go to the actual call, okay? And I am going to comment out the original code so that I don't lose it. And now we change the 3 to a 2, which is the smallest value of n in order to end up with a 21 or 15 in hexadecimal. So I'm going to say to do, okay, you remove this after testing, okay? And then we test it again. In other words, I am looking at the boundary cases and make sure the code works for the boundary cases. Because just because it works for one case, like 3, does not mean it works for the boundary case. But if it does work for the boundary case, chances are it's going to work for all cases. So now we go back and say, okay, it is still 115, perfect. Okay, so now I have to test it again with the other boundary case, which is 1. So now we go back and go to the source code again. And this time we are going to change it to just 1, because if n is 1, we should go for the then case, which in this test code is supposed to return a 52. So what is 52 in hexadecimal? Same thing. Okay, you divide it by 16. Whatever the quotient is the first digit in hexadecimal. So in this case, 52 divided by 16 has a quotient of 3. And then the remainder is going to be the other digit, the one to the right-hand side. So 48, so we have a 4 left over. So it should be a 3, 4 in hexadecimal. Are we doing okay so far with the base conversion? In terms, at least the concept, because at this point, you really should know how to do base conversion, at least conceptually. When I explain the thinking process, you should understand it. Okay? Because if you don't, that means there might be other things that you may not be understanding in this class. Okay, and that would have definitely bothered me if I were you. All right, so we are now going to test the code, making sure this is a one, make sure we save the code, and then we run the code again. So this time we should see FE to be updated with what, 434, instead of, yep, there we go. Okay, so all is good. Are we doing okay so far? Okay, because I am methodically testing the code as I only introduce a few lines at a time. Because this way I don't end up with 20 or 30 lines of new code and have no idea why the program is not working. Okay, and every time the program is working, if I were actually doing the coding and I'm actually doing the homework assignment like you did, I would use GitHub or some tool like that. So I would save an earlier version that I have verified to be working, and I would comment, okay, what is working about that version, so that I know if I need to fall back on an earlier version, which one would be appropriate. Is that okay? That is all useful stuff, not only for this class, it's not only for other programming classes. This is the sort of stuff that employers are looking for. They don't want to know just that, oh, I'm aware of GitHub, I know what it is. I check out projects. Okay, well, that's great. Okay, but they want to know, do you know what the tool is for? Do you know how to use the tool? And do you know the value of the tool? All of those are important to an employer. Okay, so I'm basically interleaving subject matter stuff with non-subject matter stuff in this class. All right, so that means I now have a pretty good platform. The else is all good, the then is all good. So we are going to go back to the original code. Okay, the original code is this. So I just need to return n if for the then case. So that means the then case actually has nothing to do. There's nothing to do, but I'm going to leave a comment here. We'll just say that A is already n at this point of time. Okay, how do we know? Because when we do the comparison, this A is already n, and then the actual code is supposed to return n by itself. So that means, oh, I don't have to do a single thing because the result is in register A already. Are we doing okay so far with that? Okay, so the key to come to this conclusion or to come to this realization is you have to track what is in each register the whole time. Okay, all right, so that means I can now focus on the else case, which is going to be the messy one, right? Because we have to deal with your f of n minus 1 plus f of n minus 2. So what do? You deal with one recursion at a time. Okay, make sure it works for one recursion before you kind of work out the other one. So that's what we'll do. Okay, so we're going to change this code and say, okay, we're going to work with one side of the recursive call, okay, which is just f of n minus 1. Register A already has n in it, so decrement A is going to end up with n minus 1 being stored in register A. Now we just have to push it, decrement D, stda, and then we have to push the return address, which is the usual LDIA with .6 plus, decrement D, stda. So um, now we have the argument pushed, and we also have the return address pushed. So now it's time to continue execution at the function, which turns out to be exactly where I am at this point, the same function, which is f. When it returns, we have to do an increment d. Why do we have to do the increment d? Yep, yep, yep. We have to deallocate from the caller's perspective the argument, but from the callee's perspective, it is the parameter. Okay, so you're correct. So we have to do the increment D to get rid of the argument. Otherwise, the stack pointer is not going to be balanced. And then we have a register A containing the return value. So according to the modified code, okay, so I'm just going to copy and paste this here. Okay, so we are not going to we are not implementing the full thing. We are basically ignoring the second part right now. Okay, this is what we are actually implementing at this point. Okay, so okay, I think I got it done already because if you look at this, whatever f of n minus one is returning is already in register A, and that became my own return value, so I don't have to do a single thing. So that means by the time we get to line 38, the recursive call is done, and we're free to proceed. Yep. So n minus one is not in register A. N minus one is n is in register A initially. So that's why we need line 31 so that A is now n minus one, and then we push it on the stack. Yep. So once again, I'm not commenting my code, even though verbally I'm describing everything, because I want you to do the commenting, okay? Because as you go through the program and then you add your own comment, that is when kind of it gives you a second chance to practice and let the ideas sink in. Okay, so the knowledge is already here. The knowledge is already being recorded. Let me just double check. So the knowledge is being recorded, okay? But I'm not putting it into the comment of the code so that you have to do it, okay? Well, okay, I shouldn't say you have to do it so that you can do it. It is always an invitation, never a command, okay? Because at the end of the day, it is also not my grade. Okay, so I'll let you guys evaluate whether you want to do it or not. Okay, it is definitely your freedom. But some people do not have to do it. Some other people probably should do it. All right, so just with this code, okay, I can now go back to the main program and make it go for one single level of recursion. Okay, because two is going to trigger it to go for one recursion. And you can also change the C program accordingly as well. So in other words, what I meant is if you go to this folder, you can now go to the C program, mess it up, okay? But do it the same way. Okay, so we want to edit anyway, like so. And then we want to change this code, okay, once before you make any changes, just comment out the original code, and then you say, we are taking out the second recursive call, and we are now replacing the argument with a 2. So this way, we can rely on the C code to model what X is supposed to have when everything is done. You can also, use GDB to figure out how many call frames should be present when this code runs. So I'll illustrate what I mean by that. Okay, gcc-g-o fib.c gdb fib. Okay, so this time I will set up a breakpoint in F. So this is one thing that's kind of handy with GDB. If you just name the function and you say I want to put a breakpoint, with that function, it automatically put the breakpoint at the very beginning of the function. So it's kind of handy, not something that is super duper important, but it is handy to know. There we go. And then when we run this program, okay, this is the first time. And you can also see, from the output of GDB, this is the time when n equals to 2. But because of the logic, 2 is not less than 2, we know it's going to go for the recursive case. So now I can just continue to run the program, okay, until the next breakpoint. And this is the second time. Okay, so there are two call frames right now. The second call frame has n being equal to 1. And this would be the last call frame because when n is 1, 1 is less than 2 is true. It would just return n itself. It returns a 1. And then the other one would also return a 1, which means x should be updated to a 1. Okay, but if you like visualization, Online GDB actually does a better job with visualization because it actually shows you in a tiny little window or a little box of the call frames. If you're using just the command line version of GDB, you can still do it. You can use the command called BT or backtrace. So this shows you how many frames should be on the stack at this point of time. We have 3 frames. It's counted in the reverse way, okay? So frame 0 is what we see at the lowest address in my visualization of the stack. That's the second invocation of F. Then we have the first invocation of F, and then we have main. So this tells me that the picture of the stack based on this particular program should look something like this. Okay, we would have this being a 0, 2 because we changed the program, so this is now 0, 2. Okay, one more time, 0, 2. And then we have another invocation where we have 0, 1 over here. This is n of f again of the second invocation of f. And now we have a return address from f back to f. So this would be a different return address because it's from f to f itself. And I have no idea what that is, okay? And then the stack pointer should be here if we stop in the second invocation of f. Okay, so I'm gonna color code this again. Okay, use another color here. Okay, there we go. All right, so this should be what the stack looks like in the second invocation of f. So I would go back to my code. Okay, go back to the assembly code right here, and then I will put a halt instruction so that I freeze everything when we are going for the non-recursive case. So the non-recursive case is the then case, which is here. So I will put a halt instruction here. That halt instruction will freeze the frame so that it would look like this. Are we are we understanding how I am setting up the program for debugging purposes, for verification purposes, I should say? So we're good. All right. So we're going to let the program run, okay? And we want to focus on, are we going to see all this stuff on the stack? So we switch back here and make sure it is saved and then run it again. All right, there we go. And then we switch back to the trace. And then we look at what is on the stack. Okay, location FB is supposed to be 0, 1, and location FB is supposed to be 0, 1. And then one more thing, okay, location FA is supposed to be the return address from F back to F. So we go to the Assemble tab to make sure that is the case. So now we have location 2, 1 over here. It is right after the JMPI instruction inside F itself. It is the correct return address. So at this point, I have verified the stack looks like this, as it should. And now I can continue, I can remove the halt instruction. So it finishes the computation, in which case, x of main should become 0, 1 when everything is done. So I go back to my source code here, and then we just remove the halt instruction, and then we just let the program run again. Okay, save it and run it again. And then this time we should see a longer trace because I let the program finish completely. And then we should also see location FE storing a value of 1. Go to the analysis tab. Yep, that's exactly what we're seeing. The program terminates at the halt instruction. The stack pointer is fully balanced, so we are good. Are we good so far? Are there any questions? So I have successfully verified that the program works in the recursive case. Okay, now even though it doesn't really do what it is supposed to do in the recursive case, it is okay, because I just know that it is now doing the recursion correctly. So this part is the most difficult part of this entire programming exercise. It's how do you add the second recursive call? So let's go back to the code and figure out why this is the most difficult part. Because most people think if I can do one recursive call, what is the other recursive call? I mean, it's just kind of repeating the same thing. Well, not quite. Okay. So now we are ready for the recursive call. So we need to do a recursive call of f of n minus 2. This is where f of n minus 2 is supposed to go. And we take this out because now we are actually trying to implement the original code. So you go like, okay, first of all, how do I get n minus 1? How do I compute n minus 1? You go like, well, since register A was n minus 1, when we push it on the stack, we just need to decrement n one more time, register A one more time. That is not true, okay? Because register A is specifying the return value, okay? So register A is not n anymore. Is that okay? So how do we get n minus 1 in this case? You guys tell me. Okay. Okay, so you are trying to save register A at this point into a different register. Okay, so unfortunately, it does not work, as you might have figured out. The reason why it doesn't work is also because of the caller-callee agreement. The caller-callee agreement says what? Yep, exactly. The callee has no obligation to maintain the values of the registers from the caller's perspective. Every single register can be overwritten. Yep, yep, yes. I know, but you cannot since we did not specifically name a local variable in the C code, so it does not exist. Okay, so, but let me finish up the actual recursive call first, and then we'll try to answer that question. So the first thing is this approach does not work. Okay, this approach does not work due to the caller-callee agreement, because in the agreement it was very specific that registers A, B, and C will not be preserved by the callee. So you cannot do this. Okay. All right. So if that doesn't work, we'll just have to recompute the whole thing. Okay, that's the worst case scenario. We just have to recompute the whole thing. LDI A with F underscore N add AD and then LDAA. Okay, fine. No big deal. We just recompute the whole thing. Now register A has N again. Since we need N minus 2, decrement at decrement A. Decrement A. Now A is N minus 2. We push it on the stack. And then someone at this point is going to say, but Tag, stop, because register A on line 38 is the return value of the first call to F. We cannot just overwrite the register A, right? Okay, well, let's just say that, yep, you are right. Okay, we should be using another register. So just change all of these to register B. Okay, and then we are now careful. Okay, we push it on the stack. So we decrement D stdb. So we have just pushed n minus 2 on the stack right now. And then we now have to push the return address on the stack, which is LDIB. Okay, we are now careful not to overwrite register A. As it turns out, that's all useless. So all this effort is completely useless. Okay, but we'll see why that is useless. Decrement D, push that thing on the stack. So now we have pushed the return address on the stack, continue execution at F, increment D after this is over, and now you have another existential crisis. Because let's just say, let's just say that register A is preserved, but it is not possible because register A also should be storing the return value of f of n minus 2. Register A cannot be doing both at the same time. It is one single register. So that means I just lost the return value of f of n minus 1. So how can I fix this problem? Yes. hmm Well, actually, that may not work either. Okay. So the way to fix this problem is actually in one of the earlier labs. So one of the earlier labs, I cannot remember the name of the lab. I think it is params and return value. I could be wrong, but I think that is the case. Let me see whether I put a reference to that lab over here. I'll just take a quick look. Aha, haha. It says right here, hint, the params and return value lab may actually be quite important for this assignment, not the lab, but the assignment. Okay, so now I'm pretending that I'm a student and go like, huh, if text says this, maybe it's worth my time to investigate a little bit. So now I go back to the earlier lab and reopen this lab. You can always reopen the lab, by the way, okay, to at least to see your answers, okay. And then I go through all the questions, okay. Since I'm the professor, I don't have the stored answers here in this case, so I'm just going through this. As it turns out, the very first question is giving you the answer to that question. Okay, so now we go through this code, okay, and then we try to find out, so where's the solution here? Okay, so let's go through this code and ask, I mean, all of you answered this one correctly, right? So did you just run the code and find the answer, or did you actually try to figure out why that is the case? All right, so let's take a look at this code here and see and try to find out what it does. Okay, so every line is important. Okay, the no op is important because that allows you to use it in River Spider. And then LDI D0 is just initializing the stack pointer. Important, but not too important. LDI dot 6 plus, decrement D, STDA, that's pushing the return address. JMPI to 5, that's the actual branch to the function 5, which does not take any arguments. Decrement D, STDA, what is that doing? We are pushing the return value of the first call of 5 on the stack. It is the same thing. It is the same thing as creating a local variable, except it is not named. Yep. So it has the same effect as using a local variable, but you're just using it, you're basically consuming stack space as necessary without using a local variable. Because in the C code, there was not an extra local variable, so I'm not using an extra variable in the assembly code either. I'm just saying, okay, this I need later on. I'm just going to push it on the stack. All right. So that is the key. Okay, you push the return value of the first call on the stack. Then you can retrieve it later. Okay, so according to this code, how did I retrieve it? So these two lines are pushing the return value of the first call of 5 on the stack, and then I called the second time just like usual. Okay, so these lines are really just for setting up the return address and then calling 5 again. So when 5 returns at this point, register A would contain the return value of the second call of 5. So I go to the stack and I pop the return value of the first call of 5 into register B, and then I add those two, and now we have the return value of the first call of 5 in register B and the return value of 5 in the second call of 5 in register A, add them together, and that's how we end up with 10 as the answer to this question. All right. So the solution is right here, okay? And that's why I point people to go back to this one to go like, okay, yeah, the clue to the answer is right here. So now we go back to the code here, knowing that trick. So now we go like, okay, let's push the return value of the first call of 5. So the first call of 5 is right here. Okay, so we could basically say we push that here. So we just go do a decrement D and then a STDA, and most people go like attack. Line 37 and line 38 cancel out each other, so you don't need to do either. Well, yeah, you're right. Okay, fine. But the key is I am actually what line 39 ends up doing in this case. It is overwriting the space that was used for the argument, and it's overwriting that location with the return value of f of n minus 1. It's just reusing the same location without first deallocating and then reallocating. So if I were you though, I would just do the usual thing because conceptually the increment D has significance. It is deallocating the argument on the stack. And then also conceptually, line 38, the decrement D is also meaningful because it is reallocating, even though it's the same location, it's reallocating the location to push the return value of f of n minus 1. Okay, but this code is not going to be correct. Okay, it's going to break. So we're going to take a look at how it is breaking and how to debug it. Or do you guys just want the solution? It's up to you. Hmm? Debug it? Okay, let's do it. So let's go ahead and just do it the way it is and then figure out it's not right. Okay, something is wrong with this. So we'll go ahead and save it. Okay, and oh, I need to make sure one more thing. We need to make sure it is still going for the recursive case. So yes, it is still going for the recursive case because we have a 2 initially. So now we want to emulate this execution. We do have 2 points of recursion now. In other words, okay, let me finish up the rest here. So after the return from the second call, I need to I need to pop the return value of f of n minus 1, which is sitting on the stack right now. So I need to do LDB and then increment D because I'm popping. Okay, this is for popping f of n minus 1 from the stack into register A, into register B. So now I can do a add AB, which is adding register B to register A, and that would be the result. Okay, that is supposed to be the result. Okay, all right, save the code, run it. It is possible that by accident it might actually do the right thing, but I don't think that's going to be the case. Why is it taking so long? Hmm. Let me check on the other side. Yes. It's not running yet. Okay, so it's complaining it did not assemble correctly. So I introduced a bug in the program. All right, we go to here and it says unrecognized something something. Unrecognized 5 on this line. That is really weird. Okay, well, let me just kind of run it one more time. It is possible. It's just a synchronization problem. No, it is not. Oh, no, this time it ran, right? Validating. It did not assemble correctly. It still does not assemble correctly. Huh. Oh, I think I messed up the assembler in some major way. I probably typed something on the keyboard when I'm not supposed to. So if this happens to you, the quickest way to fix the problem is to go to your version history, go to see version history over here, and just revert it back to yesterday. Okay, that would be fine because whatever I did wrong was happening today. So I just restore to this version and then just rerun River Spider. It should be fine. All right, so let's go back and run it again. Okay, object code is good. Okay, so that fixed the problem. And this time it's going to take a long time because I think it's going to get into some kind of infinite thingy, okay, which makes the analysis tab really, really long. Okay, so now the question is, how do we debug this? So once again, it has to do with tracking this down. Okay, so when this is done, okay, when the call of f of when this is so this is a little bit harder to explain because it's a dynamic change on the stack. So when f of 1 is done, it is supposed to go back to the caller, the first invocation of f, and then it's supposed to call again. The second call would look like this. So when this is done, okay, I'm just gonna show you what happens. So when the first call is done, which we know is happening correctly already. So when that is done, it's supposed to empty out this content, and then this location is going to store the return value of f of 1, which is actually 0, 1. That is correct. So there's no problem here. But this becomes your saved value of f of n minus 1. And then we set up the stack again so that this location should become 0, 0. And this would become the n minus 2. Okay, this is n minus 2 being pushed for f of n minus 2. And then we push the return address. Okay, so this is the return address again. This is the return address um, of the second recursive call. That's what the stack is supposed to look like. In other words, I'm supposed to see a 0, 0 overwriting location FA. Okay, so now we go back and look at the assemble tab. So do we have any questions about why this is what the stack is supposed to look like in after the second call from the the second recursive call of f from the first invocation of f? Whew, okay, okay. So we started off with f of 2. That's coming from main, right? So f of 2 is going to say, okay, I need to call f of 1. We know f of 1 is returning correctly because it is not a recursive one. It just returns 1. Okay, so that returns a 1, and that 1 should be pushed on the stack. And that one being pushed on the stack is taking location FB according to the new code. So then the program says, okay, but I also need to call f of 0. And we are trying to call f of 0. And I'm telling you that when it's attempting to call f of 0, that part is wrong. Now, when it attempts to call f of 0, because FB, location FB is already used to save f of n minus 1, that means 0, 0 as the only argument for the second recursive call from the first invocation of f is supposed to push the 0, 0 at location FA. Are we doing okay so far with that analysis? Okay, so now the question is, did I push 0, 0 at location FA? So now we go back to the assemble view, the trace here, and then we go like, okay, so far so good. This is still good, okay? This is not a problem because it was the return address, okay? Hmm, So FB is 0, 1. Okay, let me go back to the picture. FB being 0, 1, that's pushing the return value of f of n minus 1 on the stack. So that is still being okay. And then we push 4, 3 on the stack. That is wrong. Okay, I don't even need to look at the rest of the code because this place is wrong already. Because I'm supposed to push a 0, 0 on the stack as f of n minus 2. The n minus 2 should be 0, 0 because n was 2. Okay, so now the question is, how did it do this wrong? It was right up to this point, and it's wrong up to this point. So whatever the problem is from possibly from line 41 to line 47. we have 6 lines to investigate. Is that okay? But if I did not do this step by step, okay, then I would have the whole program, the whole function f to reevaluate. It's like, why is this not working? But at this point, I have narrowed down to line 41 to line 47. And even better than that, I can now track down step by step what is going on and at which point it is wrong. So you can either go backwards, starting with the last line where the problem is detected and start with line 47 and execute the program backwards, or you can start with the last point where everything was correct and then somehow things went wrong after that point. So I'm going to go by the forward way. Okay, so we start with line 41. Okay, so line 41 is going to load the offset from the base of the frame to parameter n into register B, which is 1 byte. That is correct, not a problem. And then line 42 is supposed to add the base of the frame to the offset to find n, and that is not correct. Okay, because when you look at the picture on the stack, where is n of f? N of f is supposed to be at location fd, and I'm short 1 byte. I'm short 1 byte over here. That is where the problem is. So what went wrong in this case? The problem is the stack pointer. Yes, go ahead. Correct. Yep, that is correct. So the problem is the stack pointer is no longer pointing to the base of the frame, which was usually the correct assumption, but in this case, that is not correct anymore. So from the pictorial perspective, this frame is still the correct frame. Unfortunately, once we push the return value of f of n on the stack pointer is now pointing here, even though the base of the frame is still here. They're off by 1 because of the extra push of the return value of f of n minus 1. Are we doing okay so far? Because this is actually really important. Okay, if you have a general idea of, yeah, I kind of get what you're talking about, that the stack pointer is no longer pointing to the base of the frame, then you're okay. Okay, you can still kind of listen to the lecture again, especially this part, which is kind of toward the end of the lecture. On the other hand, for people who have no idea what I'm talking about, what is the base of the frame and what is the stack pointer and how those two are supposed to be related somehow, that means those people need to study a lot more. Okay, because that is a crucial concept. There are 2 separate concepts here. They are related. One is where is the base of the frame. The second one is where is the stack pointer pointing to. Okay, they are related because most of the time the stack pointer does point to the base of the frame, but if you have any extra push after setting up the frame, then the extra push will move the stack pointer to locations that are lower than the base of the frame, like in this case. Okay, so the fix to this problem, okay, is simply to account for that and go like, oh, okay, in order to find in order to find parameter n at this point, I just need to adjust for that extra byte that we have used on the stack. So you can adjust it like this. That's one way to do it. Okay, so now we save the code, okay, and we rerun the code. So when we rerun this code, it's not going to change any sequence prior to this. The only thing it would change is simply what we push on the stack at this point, and now it is pushing the correct thing on the stack. So at this point, we should see location FE being updated to 1 because f of 2 is supposed to be 1, and it should not go for an infinite recursion anymore. And as we can find out, that really is the case. So now that this version is working, I can now retest it using f of 3 because that was the original program. So I go back to here, and then I just go to this location and then we get rid of this to do, uncomment the original line, restore that, and then we run this code again and see if it is doing it correctly. And that's going to push your lines all the way down too, because the trace is going to be slightly longer than before. There we go. Do 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 do. Yep. So the program is now correct. All right. So that's the process. Okay. I understand that I can do this in one lecture session because I already kind of know this stuff here. But the process that I went through to do this is emulating what you should also be doing. Okay, because I could have just given you the solution, right? And send it to you guys through the announcement and not to talk about the whole process of how to do this. The process itself is more important than the end result. The end result is just an excuse to get you guys to practice what you're supposed to be practicing. It is the process. Are we doing okay so far with this? So did you guys struggle a little bit with this program? Okay, that is good. Okay, because as you struggle, that's how you study. All the labs add up to 20% of your grade. That means one single lab or one single turn in assignment that you need to turn in is not really taking up that many point values. But the practice, the way that you do it, the way you're trying to find out what's wrong with the program, that is important. Oh, uh, it's as long as you don't make a new actual variable, it is still consistent with the C code. This is actually what compilers do. Yep. Yep. That's the whole point of the stack is you allocate as you need and then you deallocate when you don't need it anymore. Yep. hmm All right. But you did realize, this is a solution to the problem. Uh-huh. Oh, okay. Cool. Yep. Yes, that would work too. Uh, overriding what with the Oh, I see. Okay, that's not a bad way to do it. Okay, cool. So, as long as your code is portable, and it will still work with F4, F5, and so on, and sounds like your approach is general, so it would still be fine. Okay, any other questions? I do have to mention one thing. If the program does not compile or does not assemble, it's automatically a zero. It may not work, okay? I can still give partial credit to programs that do not work, but programs that do not even assemble, I will give a zero because that means those people did not even bother to actually put it into the assembler and fix all the problems that can be reported by the assembler. So that's kind of the deal. Occasionally, I would get submissions that contain instructions that do not even exist in TTP. And obviously, those would get zeros. I wish I could give people negative scores, but I cannot. Because the only reason why I would see instructions that do not even belong to the TTP instruction set is those people try to use AI to solve the problem or try to get someone else who has not been taking this class to help them with the problem and do not even bother again to go to the assembler to check whether it would even assemble or not. That to me is like, yeah, negative score. Yep, go ahead. Were you using the AI assistant that's in the class? Are you using the one that I got a link here? Oh, okay. Because that one is actually specially configured for helping out coding in this class. It has awareness of the instruction set of TTP and also how we use the stack. So if we are talking about, where is it? At the bottom? Oh, right, ChatGPT TA. So this one is actually really aware. I try my best to get it to work with the architecture and also the caller calling agreement. It still makes mistakes occasionally. That's kind of the whole thing about GPT is it's not 100% anytime. There's always a probabilistic chance that it would just go somewhere and pull an instruction that does not exist. But for most people, it does work most of the time. All right. So there's that. And that uses up the entire lecture time, which is fine. Okay. This is exactly how I would plan to use my time, is really to demonstrate not only the concepts, but also the process of doing things. Are we doing okay? All right. So everything is still being recorded. Okay. I'm not missing anything. So today's lab is on structures again. So we have talked about structures, but I don't think we have done anything with structures. So we are doing the basic structure one. Okay, this is the one lab that we are doing today. And the access code is struct. Okay, not very creative today. It's just struct. And let me open it up, publish. There we go. So you should be able to access it now. And this one does require the use of online GDB, so you can use online GDB if you want to, or use whatever tool is installed on the computer. You just need GDB somehow. Okay, online GDB is the quickest way to do it. All right, so I'm gonna go back to my office, get some water, and then we'll come back here. Oh, I need to turn off the recorder.